right now. So it's recording. So welcome everybody. We are 108 people here in this first session in this series, in this seminar, in this series of seminars on machine learning and optimization. Unfortunately, coronavirus crisis is giving to us many bad things, but on top of this, it is also given to us the opportunity of meeting again a lot of colleagues, friends, and experts in the bridge between machine learning and optimization. And we hope this you will all enjoy this series of conferences, which is starting today. This is a joint initiative of the Institute of Mathematics of the University of Seville, where I am now. We have 9 degrees right now, and also the CBS in Denmark. The link between IMUS, Institute of Mathematics in Seville, and the CBS, the Copenhagen Business School, is in fact an European project. The project NEEDS. This is the game we have made with the name of machine learning NEEDS, mathematical optimization. And in fact, Dolores Romero is the leader of this European project, which is supporting this initiative. So thank you all. We are 124 people now. Thank you all for being here. Thank you, Ilker, the first speaker, and I give the word to Dolores right now. So Dolores, please.
Yes, so I will take a couple of minutes to introduce Ilker Birbil. It's a pleasure for me. So Ilker did his studies in Turkey, and then he moved to do his PhD to the USA and did his postdoctoral studies in Erasmus University. And then he went back to Sabanci University, and in 2018 he went back to the Netherlands to take a chair, and I don't want to get wrong the name. So he's a chair in data science and optimization at the econometrics department of Erasmus University. So for me, it's actually a pleasure because we have crossed in different places. So and something that joins us is Erasmus. So he has written a lot of papers in mathematical optimization. His expertise is broad, including global optimization, but also mixed integer linear optimization. He has published in leading journals in our areas, such as EJOR, mathematical programming, management science, mathematics of operations research, and he has received awards for his research, also for his teaching. He has a long list of service activities, and today he's going to be talking about interpretability. So it's a topic that, again, it comes very close to us. So we are very happy that you will be the first to open this online seminar series. Thank you so much for accepting the invitation, and the floor is yours.
Oh, thank you very much. You're very kind. Dolores, hold on, I'll just share my screen. And that is this one. I hope everybody sees that. I don't see you anymore, so I might need just some confirmation. I hope it's fine now.
Yes.
All right, excellent. And thank you. Really, this is an excellent initiative, and I'm really grateful that I am the first one. I'm a little bit scared also because now it's really crowded here, which is a good thing, of course. And I hope I'll be able to entertain you with what we have been doing lately with Hakan. Hakan is also at Erasmus University. And maybe this is the first time that I should also tell this. And from the 1st of May, I'll be in University of Amsterdam. So I'll be moving there. But the Netherlands is a small country, so we will be carrying on with our research with Hakan. He's an excellent researcher. And I'll be presenting stuff. I must also say that he has done many things here. So his name should be probably right next to mine, but he insisted that I should have my name there. And thanks again, Emilio, Dolores, for this invitation. And today it's the first seminar, and I'll be talking about this topic which is at the intersection of data science and optimization. And I'll be just skimming through several things regarding the optimization part, but I'll try to give you the main idea. Hopefully I'll manage that, and that I will just consider myself successful if I do that. All right, with that I start. This is me, and I live in Utrecht, and as Dolores already said, I live in the Netherlands, but nowadays it mainly means that I live in my house. I don't really go out that much, so it's kind of strange. So I decided that all my presentations, while I'm in this lockdown, I'll be using this slide, and that's what I'm right now doing. And what's the topic about? The topic is about interpretability, something Dolores already mentioned. And why I am interested in that, or many people are interested in that, because we know that machine learning and artificial intelligence is taking a huge recognition nowadays, right? We have really powerful predictive models, and these models are really coming up with excellent solutions, excellent predictions. But there are a couple of issues here. First of all, the old statistical tools that we have been using for a long time, like decision trees or linear regression and so on, we do like them, not because that they're really effective in predicting, but they also give us some explanations when it comes to doing some sort of inference, or just telling to other users who are not really knowing what we are doing. But as an analyst, we will just say that these are the conclusions, and these conclusions comes out of these let's say, reasons. But that's somehow really going down the drain when people are starting to talk about these huge deep learning models, or also random forests and so on, things that I'll be talking about. But lately, people from different fields, and mainly I would say people from mathematical optimization, they really started moving into describing what's going on with these black box models. And it turns out that this is also quite important to explain these models, because as you can see, there are many also interests from the community in general, from the society, and also from the news people. And we need to be able to explain these models, and there are things we can do. And here is an old example from Washington Post, and this nice lady, she's a teacher, and she was expelled because of an algorithm that decided that she's not really a good teacher. And it turned out it's a wrong conclusion, because her students and also the families of the school, they were really fond of her, and they thought that she was really good. So it's one thing that we are really causing these troubles with these algorithms, but we should be able to explain in certain cases, like in this credit scoring, why people are not qualified for a credit, or why people are really laid off. Now, there is this thing, of course, and from more mathematics point of view, or statistics point of view, optimization point of view, we are always after accuracy. I mean, not always, but we really go for that. But there's also this other pocket of the scale, which is about interpretability. We really like to try to push this down a little bit, if we can. And that really takes me to the outline of my talk. So first, I'll be talking about related work, and I must say that it's just some work that I'll be talking about. And these are the ones which will probably ease my, yeah?
I don't want to stop you, but I myself don't see the slides.
You don't see the slides?
No, and I think I'm reading other people, yeah, I see other messages of people. So maybe we can.
Just the first slide. We were seeing just the first slide.
Yeah.
Really?
I don't know if you were moving.
Yeah, and then it went
No,
black.
I was. That's really strange, and I will try it again.
If you stop.
I stopped, and I'm now sharing it again. Now, do you see outline?
Outline.
Yes.
I see outline.
Okay, so I'll just go back for the previous slide very briefly, because I already talked about that.
Excellent.
You also see this scale, accuracy, interpretability?
Yes.
Oh, this is new. Very good.
Okay, and before that, I had this one. I hope. Yeah, I was just talking about this stuff, some news articles. All right. So now everybody sees outline, right? I can carry on.
Yes, we do.
All right, good. So what I'll be talking about is, first, I'll just discuss some related work. I'm saying some because there's a vast amount of literature there, and I'll be just touching upon the ones that will ease me into describing our own work. And I will use this as an invitation for those who are doing mathematical optimization. I will say that the models that have been around, that I have seen so far on this topic, they are pretty easy to dive in. And with your expertise in integer programming, linear programming, I think you can really go far, and there is a lot of room for everyone. And then I'll be talking about two things that we have developed. Now, do you see the second and the third, rule extraction and rule generation?
We are still on the Washington Post slide.
Okay, I don't know what's happening because it just simply doesn't show that. Okay, how about this? I will share my entire screen.
Yeah.
Maybe this would help.
Yeah, that is normally, yeah.
Does it help?
Okay, so if you can move to another slide, then. Yeah, that's perfect. Yeah.
Do you see 2, 3, and everything?
1 to 3.
Yes.
Okay, good. So what was I saying? But anyways, I'll carry on. I'll be talking about this rule extraction and rule generation that will start with a model that we have been working on, and I'll be talking about extraction from a collection of ensemble of trees, and talk about a little bit the column generation or the rule generation structure that we have developed. I will of course show you some results and try to give you the positive and the negative sides of what we are trying to develop, and try to help you to follow what we mean by accuracy and interpretability. And then I will have the conclusion, and hopefully we will have like around 15 minutes for discussion, and I am all ears for the questions that you might ask about our research. Now I'm on the next slide. Hopefully everybody sees this. Rule-based methods using optimization.
Yes, we do.
Okay, excellent. Then I'll carry on. So when I'm talking about rule-based methods, of course, rule-based methods is a very vast field, and also from people from computer science, they have been developing a lot of tools on that. But I'll be more focusing on people using optimization. So that will be the focus of this talk, and that's basically what we are doing here as well. And what do I mean by a rule? For those maybe who are not that familiar with the topic, we are really talking about some if-then conditions. So an example will be if the age of person is higher than 25, and she did get some credit in the past, then we are going to accept it. So this is a typical rule that people also easily understand in the business world. One typical example is, of course, the decision trees. The decision trees is, if you really want to take a look at it, it's just basically a bunch of rules put together in a nice manner. And if you really follow the, just a second, for instance, from root node to the leaf node, that will be considered as a rule. So if this is our data, by using these different rules, certain data points will fall into different leaves. That is a typical decision tree. And these are the labels of the data, so some triangles and some squares, some circles. And when we are talking about a rule, it's just nothing but a path from the root node to the leaf node. People do like decision trees because they are very easy to understand, and they are also occasionally they're quite powerful in terms of accuracy, and they're also easy to interpret. When I said that I'll be just walking through a couple of examples that I also liked reading myself, and I think that will also give you some hint. And there's this example in 2013, Malitov and Varshney. They looked at this problem of how to really learn this or to extract or generate these rules. They came up with a model which really tries to shape this problem into the compressed sensing. So if you're from that area, that will look very familiar, but the main idea is we are going to really come up with these atomic structures of an if-then rule, okay, and they're trying to really pick as few as possible, and they're going to use this for a binary classification. So if you think about a labeled data, so some data, the data is already labeled at ones and zeros, those are the two labels, binary, and then they're trying to pick a bunch of these atomic structures to form a collection of rules such that the sample the training data, the data that they are using to really obtain this WJs, the training data is properly matched, ones and zeros. But of course, this is an integer programming problem, and then they also propose to solve a linear programming relaxation. And if you look at this problem, something I also mentioned, it's less than 10 years ago, a paper which appeared in a very influential conference, and it's very easy to explain to our students. For anyone who knows a little bit linear programming or optimization, they will be able to understand that. And another paper from more the computer science community, and they're trying to learn these ORs and ANDs. And ORs and ANDs, if you think about it, ORs and ANDs are the basic structure to form these if-then rules. And that was in 2015. I know that this looks quite a bit hassle. It's a large model, difficult to understand. But the main part that I wanted to mention here is, although it looks really complicated, but if you really follow the paper, they're really talking about solving this problem in order to minimize the misclassification. So that is about the accuracy. And they're trying to come up with some sort of interpretability in the sense that if we have fewer rules and the rules are not super large, so I'm talking about many ANDs within an if-then clause, if we don't have that many of those, this could be considered as an interpretable set of rules. But the problem itself is very hard to solve, this particular problem, because it's an integer problem. Now, a very recent paper that I also like very much myself, I even asked my students in bachelor, for their bachelor project in Erasmus University to replicate these results. This also appeared in a very influential conference from the computer science community. And in this case, now we are really moving closer to what we are also discussing here. And the model that Dash, Günlük, and Wei gave is like this model, where they're really trying to come up with optimal set of if-then clauses, like I'll be showing soon what we're also doing. But in their case, they are generating these if-then clauses, and they're also going after accuracy versus simplicity. If you think about the scale that I have shown on the interpretability side, simplicity somehow, not somehow, but I think it also reflects interpretability. Now, for small instances, they solve this IP, integer programming problem. As you can see, they're just selecting these guys. So there are 0 and 1 decision variables. For large instances, they're using column generation after relaxing the problem. And here is their pricing problem they're trying to solve. And the pricing problem turns out to be also a binary problem, but there are things that we can do. Within a reasonable time limit, I think an hour or half an hour, they were able to solve problems. Very nice paper to read. Now, from here, what was our objective? Hakan and I, and before that, we also had some other friends that we talked to on this topic or related topic. We said that, okay, can we come up with a simple model? Okay, but not only it is simple, it will be fast to solve. Within, let's say, seconds, we'll be able to obtain a solution and easy to implement. So can we use some existing packages? If you think about Python, R, these are more or less the de facto standards in data science community. These are using a lot of packages. And nowadays, as some of you might already know, if you want to really, let's say, run a random forest, it will take probably 3 lines or so. It's pretty simple. But meanwhile, we have to also make sure that we can also somehow push the interpretability pocket of the scale down so that it will be more balanced. And that takes us to this rugs and rug. And the first one is for rule extraction, and the other one is for rule generation. Now, going back, remember, this was the decision tree that we are talking about. As you can see, we have a bunch of rules, and there are also many leaves, and each leaf clearly corresponds. Each leaf corresponds to a rule. Now, for the sake of this presentation, I am going to assume that I'll be dealing with binary classification. But the models that I show you and some of the results for multi-class classification, in fact, we can even extend it to regression. Okay. But for this talk, I'll be just assume that these are already labeled, and each data point is labeled as -1 and 1. Okay. So, for instance, these triangles will be -1 and the circles will be 1. That type of labeling. And what happens if I have an out of sample? And what does out of sample mean? That after you obtain such a tree or a model, any model that you can think of, from machine learning, a supervised learning model. After training it, somebody gives you a data, and then you have to, that is out of sample, you have to decide which one should it be. And for the decision trees, it's the majority voting. Okay, what does it mean? For instance, if you really end up the test out of sample that you give me, it really ends up in this leaf, then I'm going to check what happens. Oh, okay, I have 2 triangles and 1 circle, so it should be a triangle. And that I am going to denote with this structure. J corresponds to a rule, and I corresponds to a sample. All right. Now, decision trees are nice, very interpretable. People also like them quite a bit. Then there is also this other end, which is the random forest. It's an ensemble of trees. So why would I really go there? First of all, in this case, if you have a random forest, you again use this classification with majority voting. What do I mean by that? If you give me an out of sample, it really falls, suppose that in this leaf, and in this case, it falls into this leaf, and here in some other leaf, and I'm going to really, and I'm really looking at whether it will be a -1 or 1, I'll do the majority voting as before. We do like the random forest because it really pulls down the variance and the accuracy goes down, accuracy goes up, excuse me. But unfortunately, we now have thousands of rules, as you can imagine, because if you really think about all these leaves, for a forest, we are going to have thousands of rules, and unfortunately, interpretability goes down. And this is not about only the random forest. Another very powerful method is based on boosting. But this time boosting with, let's say, decision trees, which means that instead of having a collection of independent trees, we are going to have a sequence of trees really built in tandem. So building this tree depends on building this tree, and so on. These are also extremely powerful methods. And how do they really classify? They classify with classifier weights. In this case, a classifier will be just a tree. What does it mean when I am really in this case, when I'm classifying, I was just using majority voting. But here, if I am deciding that it will be in this, with this rule, with this, let's say, leaf, the weight of that leaf will be really associated with the weights assigned by the boosting method. So the weight of this tree can be, for instance, larger than that one, and maybe this one can be really larger than the very last tree. So each tree has a different weight instead of having the same weights in random forest. So, good. So we know that there are these methods we can use. Now, this is my drawing. Don't take it as the literal correct thing, but I think that will give you an idea where we're really heading. Now, if you want really high interpretable models, go for a decision tree, but they turn out to have less accuracy. Not always, okay? Not always, but they have usually less accuracy. And if you want to really increase the accuracy, then you have to sacrifice from the interpretable. You do sacrifice from the interpretable, or you may. And then we have ensemble of trees, okay? Then the question becomes, if you want to really just both the accuracy and the interpretability, we have to be really coming up a model where we can interpret these guys. In fact, maybe we can also later on think about how we can generate only the leaves instead of having all these ensemble of trees. That's where now I'm trying to really take it. Now, going back again, remember, these are how we are going to use the majority voting. Okay? And this is a subset covered with rule J. So if you give me this rule that is really marked in purple, and that will basically classify only these 3 points, okay, or cover. Okay, if I have a decision, random forest or an ensemble of trees or many trees, if you give me somehow, these are already trained, then I am going to have many of these rules, and I'm going to denote it by J, and this J will appear now and then in my presentation. Now, can I really do some sort of prediction with the rules in J? I can. Basically, this is how I'm going to really work it out. I'm going to first of all look at this particular rule J, okay, and look at the items that it will cover. This example, going back, it will be just these 3. So if you think this Aij, for this j, which is this rule that you see in purple, only 3 of the samples will be 1, all the rest will be 0. Okay. And I'm going to also assign a weight for the rule, because I will have many of those rules, as you can see, which will cover those points, let's say these 3 points. And for each one of these rules, I'm going to assign a weight. That's the main idea. Then by looking at the sign of this summation, this weighted, if you will, this average that you see here, I'm going to look at the sign, because remember, I am doing binary classification, so it will be either -1 or 1. Okay. Now, how do I measure the loss? Because somehow I have to evaluate my performance, and the performance will come with this simple calculation, super simple, and I'll show you why. Because if you look at this yi is the label of the data. Let's say that this is the training data. It's already given to you. So if it is 1, and the prediction with that rule, particular rule, is 1, this is good. If they're both -1, this is also good. I like them. If they're in the reverse order, so -1 to 1, 1 to -1, this is something I don't like. So which means that if I really look at this value, only just this value for a particular sample, I really want this as small as possible. What do I mean by that? Because if they're both 1 or -1, this will also become 0. Otherwise, this summation will become 2. So I do want to minimize this total loss. Okay. Now, I just shorten my notation because it really looks hard. Yeah, you don't see it?
No.
All right, I don't know how to really do that, because I'll stop sharing and come back again.
Yeah, thank you.
All right, where were we last time? Do you remember?
It's that it has happened several times, but we were carrying on, but this time it was a little bit longer. Sorry.
Yeah, no problem. The thing is, of course, I don't really see the screen myself.
Yeah, I didn't want to interrupt you so much. So.
No problem. Now, do you see the screen? And
yes, we see the screen.
Yes, yeah. Total loss.
How about these? Have you seen these ones?
Stop. This one is the new part. Prediction with rules in J, and we did not see the prediction.
Okay.
So we were exactly on this point.
Okay. All right. Okay. Last time I lost you. You were on this slide. Am I right?
Yes.
Okay. Then I'll do this quickly once again. So here is how I am going to make a prediction for a particular sample, and which will be, of course, -1 and 1. For that, I'm going to take the sign of this weighted average. Why is the weighted average? Let me try to repeat. So this Aij that you see here, it basically says that if you give me a particular rule, this Aij just tells me whether that particular rule covers that sample that we're talking about. If it covers, then it should be really involved in the calculation. But of course, not all the rules are the same, so I need also weights for the rules. If you give me these weighted average that you see here, which will only involve the related rules for that particular sample I, that will be my prediction. Now I am moving to the next slide, which shows the total loss, and I hope everybody sees that.
Yes.
Excellent. Okay, so how do I calculate the total loss? The total loss will be mainly, if you look at this yi, which is nothing but the exact label of the sample, and this is what I predict, this summation that you see here. Okay, that will be this summation. Now, if it is 1 and I predict it to be 1, that is good. If it is -1 and I predict it to be -1, this is nice. If it's the other way around, I try to really avoid those cases, which means that if they are really reversed, this part will be sort of -1, and 1 minus -1, this will be 2. So whenever this value is 0, I am quite happy. So which means that I will try to minimize this total loss evaluation. And to really simplify my notation, this part I am going to call it as aij hat, this part that you see here. And this is just probably operations research 1 undergraduate level trick. If you give me a maximum of 2 linear functions, as you see here, I can just introduce an auxiliary variable, which is vi in this case, which should be equal to this max, meaning that it will be larger than both values. It will be larger than what you see here, and it will be larger than 0. That's what I exactly wrote here. All right, and I'm moving to the next slide. Everybody sees the next slide?
Yeah.
All right. Okay. Thanks, Emilio. I need that. Okay. This is the model that we are proposing to solve. And a couple of things I'll walk you through. First thing, this is the total loss. Remember, we did this already. I called this part VI, and summation of them will be the total loss. That is this first component of the function. We are trying to minimize. And there is this part that you see. For each rule that I am going to pick, this is the weight corresponding to that rule, and I am going to really assign a coefficient, which is a positive coefficient, and this positive coefficient can play the role of sparsity. It can be about the rule length. So remember, we are also trying to obtain rules which are not really too long. It can be also classifier weights. This is also crucial because I said that, for instance, with the boosting methods, they have also classifier weights. So if a particular rule comes from a certain classifier, there will be an associated weight. So I might be also using those weights to decide upon this coefficient. And this could be also number of false positives, which is extremely important, for instance, in medical diagnosis. We want to really have less people who will be diagnosed already they're healthy. We are going to just call them sick. Those are the false positives. And this might also, so this constraint, the very first set of constraints, and this one was clear. This is about the weights. And this one may look a little bit strange, but remember, we are dealing with rules here, not classifier. So the rules that I'm going to pick, I am really using a handful, hopefully a handful of rules, and those rules may not cover the data set. So we are adding a coverage constraint as well. So here it is aij hat. This is about the accuracy. This is about the coverage. Now, this is a linear programming problem, and it's always simple and fast to solve. We can really solve very large-scale problems quite efficiently. And the model itself is, I would say, super elementary to understand. Now, I am going to call this problem PJ. The P stands for problem. Why J? Because as you can see, all this discussion here depends on the J. J is the rules that we are going to use. The set of rules is denoted by J. That's crucial. And how do I get that J? Because I need a bunch of rules. And remember, we already have random forest and boosting. So all our discussion so far boils down to really cherry picking. So these are the cherries. Now, those are nothing but the leaves, okay? Low-hanging fruits, if you like. And I'll just try to pick them up with the model that I have shown you in the previous slide. And this I will call rule extraction. Super simple idea, and that's why we call it this rule extraction, and the rocks will be the algorithm itself. Now comes the implementation part, because I somehow claimed that it will be simple, fast, and probably easy to implement. Now, this is how you really, but I said that it takes 3 lines to really run in a classifier on Python. And this is how you really include random forest classifier and AWS classifier, boosting and random forest. And this is what we have written, just one simple file where we implemented rocks, that is the rule extractor, and you're going to just import it from this classifier. So very similar to what you would use with sklearn, which is the machine learning package in Python. Okay, this is how you train a random forest. There are a bunch of things that you can enter. That's why I have 3 dots here. But you just train a random forest, you just create a random forest classifier and train it with fit. Now we do the same with rocks. Rocks classifier is a rule extractor, but of course it will be needing a bunch of rules, right? Remember, that's set J. And that comes from the random forest which we have already fed. So in a way, we are trying to reinterpret the random forest classifier with rule extractor. And we can also talk about the rule length cost because we can use those CJs, which were the coefficients in the objective function. Now, I can do the same with AWS classifier. First fit it, obtain a collection of trees, and then give this to, again, the rocks classifier with just using those as J. And this time, I will also use the tree weights because those are the classifier weights that I could have used. That's nothing but just to adjust CJs, the coefficients in the function. And this, as you can see, this looks exactly the same. This is how you were going to use the trained random forest for prediction, and I'll be using, for instance, the RAGRF, something that I really, so this should be an X. My apologies, this should be an X, RAGRF or RAGADA. Okay. And it's very easy to implement with this setting. Now, the next question is, does it perform well? And I'll just walk you through this particular plot. We are really talking about average accuracies, and we did a nested cross-validation for this particular set of problems. And this is, you don't see it anymore?
No, we don't
Frozen.
see it. Yeah.
So where were you last time? That's
The last block is the one with RF predict, etc.
you saw the code, right?
Yeah.
Okay,
Yeah.
good.
Yeah.
Okay, now you're not that far back. Hold on a second. I'll share my screen again. And go back with this. Now, do you see the plot?
Yeah.
The bar plot?
Yes,
Yeah.
we do.
Okay, so this is a random forest, ADA, RAGRF, the rule extractor using RF, trained RF, and this is the RAGS ADA using AWS. And a couple of things I really like to show, I also find quite strange and interesting. Now, here are some examples. These are about the average accuracies, by the way. The higher, the better. And a couple of interesting cases, because look what happens. For instance, the blue one is random forest. And the random forest, using all those many trees, this is the accuracy that we obtain. Okay? But it's funny, when we are really extracting rules and only just sticking to those rules, we are obtaining better accuracy. And this is happening in several places. And this is mainly between the random forest and the RAGRF. I mean, I don't see that much. I mean, I didn't really check everything in detail, but we are still writing this paper. With the ADA boost and RAGADA, this is not happening. But after, then the natural question becomes, yes, I understand that there is this thing that we have done. It's, okay, accurate, pretty good. But how about the number of rules? Right? That's somehow more interesting. And this is the average number of rules that we obtained with the methods that I just discussed. Now, this is in log scale, and I have a lot of difficulties with log scales. So I mark these parts. So somewhere around here, that's like in tens, and then you go up to thousands of rules. Now, again, couple of points. As you can see in these cases, right, we are obtaining far less number of rules than either the ADA boost or the random forest, because we are just extracting ones that we require. So these are the rules with positive weights. All the other weights are just zero. Now, it looks really nice here, because which means that for this transfusion problem or for the mushroom problem, you have seen that the accuracies are close enough or sometimes even better, and we are obtaining those accuracies with only tens of rules instead of using maybe thousands of rules. Of course, this is not the entire story. There are cases that we also end up producing many rules. But later on, I will also try to defend this position that we do have some weights for the rules which we may use. In a sense that if there is a threshold, if we just say that if the weight is larger than 0.01, only use those weights, we may lose some accuracy, but at least we might have less number of rules, which I will show later on. Now, when it comes to the average rule length, and this time I'm only comparing the RUGSRF and RUGS-ADA, extract applied to the random forest and the ADA boost. As you can see, in general, in almost all the problems, ADA boost, the RUGS-ADA obtains shorter rules, and you can say that roughly average rule length is just 3, which is also nice. Now we did something about accuracy versus interpretability. We do have some accurate set of rules, and they seem to be interpretable. Now, this was the question that I started with, and I gave a very simple answer to that. I used the rule extraction for the already trained model. But for those among us who know column generation and mathematical optimization, they're now probably just getting itchy, and because they see that we don't really need this random forest or boosting. We may even just generate our own rules and do the cherry picking again. That takes us to rule generation, which we call the RUG algorithm. So, enter column generation. Everybody sees this slide? Enter column generation slide?
Yes.
We are
Excellent.
entering.
All right, good. I'm glad. So, just as a reminder, what is column generation? Column generation is just basically telling you that if you have too many columns in your optimization model, linear programming model, and remember, we are also solving a linear programming model. If you have too many columns, in our case, it will be just number of the set of rules. Start with a bunch of those columns or the rules, not all of them. Solve the problem with the rules that you already have. Then only extract those necessary rules instead of using all set of rules. So think about it like this. There is this, let's say, 1,000 of rules over there. And among those, I will try to really pick the ones that will improve my optimization problem's objective function value. That is done by a pricing subproblem. And I think the details are not that important at this stage. But mainly, we are just going to pick up those rules which will have a potential to improve the objective function value. If we cannot find any, then we stop. If we find some, then we will carry on. Instead of solving one very large problem, you just end up solving, hopefully, a sequence of problems with less number of columns. Now, for that, I need to really give you the problem's dual problem, because the pricing subproblem that I just briefly mentioned depends on the dual problem. Now, this is the problem that the linear program that I have showed you before, and this time I am just going to mark it with a JT. Remember, I said that I am going to solve a sequence of problems, and T really represents the iteration. Okay, for instance, in JT plus 1, I'm going to have more columns. Okay, and for this problem, we can immediately write the dual problem, which is elementary again. And a couple of things that I really want to draw your attention. As you can see, for each constraint here, there will be a corresponding dual variable. And there is the structure here that we are observing, something that has been already discovered before for classifiers, by the way, which I omitted in this discussion, something called LP boost. But this is specifically applied for the rules, and we have also the covering constraint. Now, here are the set of dual variables, and this is the relationship. And remember, this is about the accuracy. Now, if you were just giving me these aij heads, I was using a decision. But now for every I, which is a sample, there is a corresponding beta I. Beta I is nothing but the dual. Now, how about I use trees with sample weights? So when I'm really doing this classification on this tree, for every I am going to use the corresponding beta I. Instead of treating every sample the same way, I am going to really give them weights depending on these beta I's. For that, I'll use the optimal beta I's. Now, what does it really say? It basically tells me that here is what you will do if you are really good in column generation. This is what you will be doing. But I'm not that good at column generation myself, and honestly, I'm not that good. So I will just use this trick. Instead of really using a pricing subproblem, I am going to use a proxy to that, and I'll be using trees with sample weights. Why do I call it the proxy? Because I'm not really using some exact pricing. I'm not really solving the exact pricing subproblem, because there were also gamma i's and so on. I am just really using a proxy to that, using only the beta i's. How about the initial column pool? Oh, that's not a big concern, because I can always generate one decision tree anyways. I can start with a decision tree, solve the optimization problem, and instead of a pricing subproblem, I am going to grow a tree with sample weights. Can I do this? Yes, I can do this, because these are already existing in all the packages that you can think of. Because remember, when I was talking about the boosting method, I said that each classifier, let's say tree, will have different weights. And over there, they're already using sample weights. So this is the same idea after all. This is simple. And I said that it is fastish, not exactly fast, because you end up solving many problems, and you may end up solving very many problems. So, but it's still fast. You're solving LPs, but many of them. How about the implementation part? This is, instead of rocks, we'll be using rock this time, and you're using, as before, exactly as you would be using a random forest classifier or the AWS classifier. And one nice thing about rock classifier is it is itself a classifier. It doesn't really depend on a previously already fit model. Of course, then you can use different costing structures for CJs that was in the objective function. And this is very easy to implement. Going now to some results. This is again about the accuracies, by the way, the higher the better. And I'll be showing you the results with random forest and AWS. And to be honest, I think that these are extremely powerful methods. I mean, many of my students are using them, and they're very good results. And decision tree is there because it's also quite interpretable, that I thought will be a fair comparison. And this is what we have developed. As you can see, the performance of RAG is closer to AWS and random forest, and better than decision trees in general. This is not always a story. As you can see, sometimes decision tree overtakes. And the funny thing is, decision tree, even in this particular example, overtakes AWS. So RAG can be considered like some sort of boosting method, and it is somewhere closer to random forest and AWS. This examples, of course. How about the average number of rules? That's where we start paying some price. As you can see, we are only comparing decision tree. Decision tree is very interpretable and produces less number of rules. And there are a few cases that we are really producing too many rules, as you can see here. And this was also a concern previously when I discussed RAGs. Now, having said that, these are the average rule lengths, and it really pays off when you start using the rule length curves. As you can see, all the rules that we are developing are more or less in all the problems. The length of the rules are less than decision trees in almost all problems that you can see. We may end up producing more rules, but the length of the rules are let's say, shorter. So we are somehow managing to obtain an interpretable model, sort of. Now, this is one thing that I really like to show. Remember, this was a concern. We had too many rules. But one thing that I said back then, I want to emphasize this once again. Now we have also weights. So for each rule that we are going to select, even if we have 100 rules, for each rule, we are going to have a separate weight. Here is a plot that we did talk about quite a bit with Hakan. And I'll just try to explain what it is. The green bar you're seeing here, they're about the rule weights. This is normalized. So the maximum weight, the rule with the maximum weight will be the very first one, and so on. So the height of bar, and this scatter plot or the line plot that you see here, that's about the accuracy. The higher, the better. Okay, it goes from 0 to 1, as you can see. Now what happens? This is the number of rules. If I really start adding the rules one by one, so this is accumulative. So I just use the first rule for classification, second rule, third rule. It seems that the first 3 rules, it doesn't change much. And with adding the 4th rule, I start a jump. 5th rule, it's getting better. When I really use 10 rules, only 10 rules among many rules, I'm getting pretty good accuracy. And here is a value that we can also report. Remember, these are rules, and I needed some coverage constraint. And that's also clear from this picture. With only using one rule, you can only cover the 67% of the samples. In this case, it's the test samples. So it doesn't really cover the entire region. But if you add more and more rules, of course, as you can see, you cover all the samples. So maybe the model that we solved, it may produce many rules, but then at least using these tricks, you can give some interpretation. With that, I'd better conclude, and I think I'm quite late. I apologize for that. So we can do all these things that you have seen in this presentation for multi-class classification and regression. That's good news. We did solve some of the problems, not really large scale, but we should really try them. But the other problems, we are also obtaining similar results. Now, when it comes to accuracy versus interpretability, and that's how I started my my discussion, yes, we did improve interpretability. We are obtaining less number of rules, and maybe the rule lengths are not that long or large, let's say. But the thing is, of course, for certain cases, it's not always the case. And we haven't tried some powerful other methods like XGBoost. It's one of the de facto standard for boosting methods. But I would guess we would obtain the similar results. There are other rule generation methods which we. It's gone again.
It's okay.
It's okay.
It's going okay.
Right.
Yeah.
Okay. Other rule generation methods we can use. We haven't tried them. We haven't really worked on the exact pricing sub-problem, but I have a hunch here, or I think it's more or less the case. Remember, we are just trying to grow a tree for pricing sub-problem, which is growing a tree is, even for the binary case, it is NP hard. So I don't expect too much from there, but we might use something else there. And we need, of course, more applications. And I believe if you want to really move into this field and talk about interpretability, we need more and more applications where this will be used. And with that, thank you very much. And I'm sorry about all these interruptions, but it's maybe because of my computer, I'm not sure. And I conclude my talk. Thank you.
Thank you so much, Ilker. It has been a great presentation.
My pleasure. Now I'm just trying to go back.
I think we have time for one or two questions. Yeah.
Sure, I'll be happy to answer it. I mean, you can always send me an email if we don't have enough time, because this is the curse of probably the first presentations.
Could I ask them?
Yes, Sinia, go ahead.
Yeah, my question is, oh, sorry.
Sorry, can I just tell one thing? Can you please mute your microphones?
I'm muted because I'm an organizer. Okay, so my question is, I know that you select some rules, and so your final tree, assemble of tree has less rules, but what is the final interpretation of classes? Could you say, for example, if H something like that and something like that, then it's class A, and so on?
Yeah, in the paper, maybe I'll have time. Anyways, let's skip that part. But when you obtain a bunch of rules, think about, let's say that you're going to have 10, 20 rules, right? And these rules will be all in that form. If age is larger than 25, and there is some sort of pass credit, and so on. So all of them will be in that form, of course, because these are all coming from the trees. Even if we are using rugs or rug, it doesn't matter. So we do obtain a bunch of rules indeed. But if you ask me, or maybe it's for the discussion, do they really form a decision tree themselves, the set of rules that we obtain? Not really. And we know that they don't form it, of course, because as I have shown you, we do obtain remarkable accuracies when compared against a decision tree.
Okay, thank you.
All right, no problem. But you're right, I should have showed you some maybe results that we obtained, but that goes in as a case study to the paper.
Could I ask you more technical question? I saw in Python you use some rooks and rook packages, but I think it's yours packages, right? It's
Yeah, they will be on GitHub within a month, hopefully.
okay. Okay, we are waiting for them.
Yeah, but unfortunately, we are not unfortunately, but we are using a commercial LP optimization software. We are using Groby. You can also use Simplex probably. That part is unfortunately not open source, but the entire thing will be there. But for Groby, if you're an academic, you can download it freely.
Thank you.
My pleasure.
Thank you, Senia. Is there any other question? As Ilker said, if not, you can always email him. I just had a very, very short one, and I don't want to take much of your time, but you do have a pricing or a proxy of a pricing. Does it pay off to basically do all the in advance? So say an explicit generation of columns that you think that they are hopefully good, as opposed to intrinsic?
You mean offline?
Yeah, yeah.
Yeah, I think you can do that. I mean, we have tried a couple of things. Since I still think use a proxy pricing subproblem with decision trees, right? One may just tell that why use a decision tree, because a decision tree also involves some randomness, right? Because it's not accurate. Can we use a random forest there? I think you can, but the main idea doesn't change. Another thing that could be tried, I think that is more related to your question, offline meaning that before starting your rule generation, you can generate many rules and start with those in your column pool. But of course, if you just start with a random forest, you're not going to use all of them, but take some with rocks, and that will be, let's say, 100 rules, put them in your column pool, and then carry on. These things can be tried, but I haven't tried them myself. No, but the main idea doesn't change much if you ask me.
Yeah, thank you. Okay, so I think the time is coming to an end. I would like to thank you again very much for taking our first slot in this seminar series. It has been very nice to talk about interpretability and the role of optimization there. And I just want to say to the attendees that I have put some information in the chat about registering in case that you just want to receive an email every time that we have a seminar or every time that we upload the videos of the seminar. As you know, this is going to be every Monday at 4:30 as Central European time. So next week we will have Bart Bassens from KU Leuven talking about fraud. I thank you, all of you, for your attention, and see you soon.
Thanks for coming. Bye.
See you. Bye.
Thank you. Bye.
Thank you. So I just saw that you finished the paper that you mentioned, and
Yeah, it's more or less finished. We are just trying to wrap it up within the next 2 weeks, but I'm very busy. I'm just pulling Hakan down, but hopefully we'll finish by the end of this month, and immediately I'll send it to you.
okay, that would be nice.
Excellent.
All right.
We'll
And
improve
I
it
don't know why there was these pauses which happened. Hopefully you can really resolve it.
Yes,
I don't know.
we will.